All right, well, I'd like to welcome everybody to today's MTL seminar series, and it's really a pleasure to have with us today Professor John Martinis. John has done pioneering experiments in superconducting qubits for decades, and in fact, he was with Michel Devereux and John Clark investigated macroscopic quantum coherence in quantum circuits in the 1980s. For his PhD thesis. And it turns out later we look back at that and we say those were the first superconducting qubits. Really fantastic. He's worked on a variety of low temperature device physics during his career, focusing on quantum computation since the late 1990s. He was awarded the London Prize in low temperature physics in 2014 for his work in the field. And from 2014 to 2020, he worked at Google to build a useful quantum computer, culminating in a fantastic experiment, which we may hear about today, in quantum supremacy, and that was done in 2019. So just some bookkeeping here. Please direct all questions to the Zoom chat channel, and we will get to those questions after John's talk during the Q&A. And with that, let me hand it over to Professor Martinis. Thank you for joining us today.
Yeah, thank you very much for the invitation. I very much appreciate talking about this experiment. I was scheduled to do it last year and COVID intervened, and it's good to be here. Let me share my screen and we can get started. People have been thinking about building a quantum computer for many decades now. Going back into the mid-1980s, even with Richard Feynman talking about it. And that's actually a Feynman lecture was I first learned about quantum computing back in the mid-80s. And the idea here is you might be able to do very powerful computations using a quantum computer. And that, of course, is quite the motivation to do this. And people have been working on it for decades and talking about the promise of quantum computing being very useful and powerful. And, we thought, well, okay, let's do an experiment to test whether a quantum computer can actually work and be powerful, even if it's not a useful problem. Just to check it on some crafted problem that it's powerful would tell us a lot. First of all, whether the basic science works, but also, whether practically are you going to hit some limitations. So that's what the experiment is about, is really testing whether when you build a big system, quantum computation works as expected. So today I'll talk about how we're building this. It was some new design. Then the experiment where for taking data for 200 seconds on a quantum computer, it would take thousands of years to check. And thus you see the computational advantage there. The reason it's working well is because you're doing computation on a huge Hilbert space. And probably the most important thing, and that's the thing I really wanted to do this experiment for, was, how did it work when you built a system? And the good news is that we can validate what's going on in a very simple way, and we don't see any additional decoherence physics when we scale. And there are some reasons it was designed well and system engineered well, but there's a reason for that working. And fortunately, everything is going well. And of course, we have to make things better, but the physics was fine. Okay, there we go. Just for maybe a few newcomers, why is it so interesting to manipulate quantum data? Classically, data is made with bits, which are a 0 or 1, and then you string bits together and do computations on that. In quantum computing, you can have occupy 0 and 1 at the same time with a quantum state, as I've given here. And what this kind of quantum state allows you to do is basically compute the result for 0 and 1 at the same time. So instead of computing 0 an algorithm and then 1 in an algorithm and getting the two results serially, you can get the results for 0 and 1 at the same time by putting it into this quantum state. Now, of course, this is very nice, but it's only a factor of 2. So, okay, that's kind of a nice academic exercise. But where it gets interesting is when you start adding more qubits. So for 2 qubits, each of them in the 0 and 1 state, you're then looking at all the possible combinations of 0 and 1. So now you're doing essentially a parallel computation of 4 states and 3 qubits, 8 states, 4, 16. And you see the amount of parallel computation is growing exponentially with the number of qubits, which is not what happens classically. Classically, the power kind of goes linearly with the size. Here it's growing exponentially. And of course, that's really interesting by the time you get to large number of qubits, and large is maybe 50 to a few hundreds, where for 50 to the 50, that kind of parallelization is enough to challenge a supercomputer. And by the time you get to 300 qubits, 2 to the 300 is a number that are more states than there are atoms in the universe. And clearly you can't do that calculation classically. So it should allow you to do some computations that's new and interesting. Now, the problem, of course, here is when you do the measurement, which you have to do with quantum, you'll only get, say, 300 bits out of it. And you have to build algorithms that, even though you're getting the 300 bits, you somehow extract the information that you needed by doing this complex calculation. So not all classical algorithms can be sped up using a classical algorithm. You have to choose them, but they're there and they're interesting. At the end, I'll talk a little bit about some of that. Now, what we're doing is lots of ways to make qubits, lots of atomic systems, atomic-like systems. We're going to be using superconducting qubits. And this is a very interesting system because that's kind of my thesis experiment, was you showed that macroscopic variables, macroscopic systems can obey quantum mechanics themselves. And this allows you to build quantum systems that I think are very nicely suited to build a quantum system. And on the left here is a picture of a qubit we've made a few years ago. The brownish is aluminum metal. Most of it's a ground plane with some structures in it. You can see it's rather large, a fraction of a millimeter. You can see it with your naked eye, at least when you're young. What's nice about it, it's macroscopic and it's easy to control. And you can scale it up just like you scale up computer chips, and you design it thinking about engineered properties using electromagnetic concepts. And all of that means it's very nice for building complex quantum systems. And the problem here is it's hard to make one really good, and we spent several decades, the whole field, figuring about that. But hopefully now that that's happened, one can scale it up and build bigger and bigger systems, and that's kind of what the era we're into. So just very briefly, talk about how this works. It's basically a nonlinear electrical oscillator at about 5 gigahertz frequency. We can choose that frequency. Basically, we have the center here, purple island, in a ground plane, and that forms a capacitor of the resonator. And then down at the bottom here, we have 2 Josephson junctions, which are just crossed aluminum wires with a thin aluminum oxide barrier between, and that allows Cooper pairs, the superconducting electrons, to tunnel through that. And basically, that gives you a nonlinear inductor. So this is just a nonlinear inductor oscillator. And in fact, this very accurately maps to a pendulum, which you know is nonlinear. As you get the very high amplitudes, the frequency goes down. And you can encode the qubits in a very simple way. Basically, the ground state is 0, okay? And semi-classically, there's no energy here, but quantum mechanically, there's a wave function to the current and voltage in the normal way you would think about a nearly linear harmonic oscillator. And then if you put 1 microwave photon of excitation in it, you're then in the 1 state, and you have energy, and a wave function is given here. And typically, the frequency difference between 0 and 1 is about 5 gigahertz. If you go to the 2 state, the 1 to 2 transition is about 200 megahertz lower than that, about 4.8. And that's enough nonlinearity so that you can just arrange the system so you always stay in the 0, 1 states, and you can get a qubit operation from that. Now, here's an example of the quantum logic gates that you can do with a single qubit. And the basic experiment is to have the system just relax to the ground state. You then pulse on microwaves for a variable amount of time, a known variable amount of time, with a frequency on resonant with the qubit transition. And you do that to change the qubit. You make transitions 0 to 1 and 1 to 0. And then after a certain amount of time, you then measure the qubit and find out whether it says 0 or 1 after that operation. And then you repeat that, say, 1,000 or 10,000 times or so to get a measurement of the probability. So when you do that, let's say with time equals 0, the initial probability of 0 is 1. Okay, you're in the ground state. And then as you turn on your microwave pulses for a variable amount of time, you start oscillating between the 0 state and the 1 state in what's known as Rabi oscillations. And this kind of tells you that it's working properly. Now, if you pulse this for 20 nanoseconds, you have a 0 to 1 state. And a further 20 nanosecond state will take the 1 state back to the 0 state, which gets you the identity. So we could call, of course, the 20 nanosecond pulse a NOT gate, okay? And in fact, you could build a classical computer system just using these NOT gates and 2 qubit gates, and you can do that. But what allows you in quantum computing is more complex gates. And in fact, you can pulse this instead of a 20 nanoseconds, 10 nanoseconds, and that takes the 0 state to this 0 plus 1 state I was talking about before. And then, of course, another 10 nanoseconds will take you to the NOT gate. And functionally, can think about this gate right here at 10 nanoseconds as a square root of NOT gate. Okay, now classically, you have no idea what that means, but quantum mechanically, it's very well defined. It's a known operation that gives you this unusual state that I talked about that's very useful. And through it's this kind of larger gate set that you're able to do the more powerful computations. And but the nice thing is you can map it into like classical like thinking just with this larger gate set, and thus build a computational machine. Now, one of the things you need to notice here is you keep on switching back and forth between the 0 and 1 state. But here at long times, you're beginning to have this wave shrink a little bit. And that's because there's decoherence effects in the qubits. It's losing its energy, it can dephase, it can have some errors in it. And this is fundamental to a qubit, that you can have errors. And you have to do very careful experiments to understand that and to improve it, to make sure you have enough coherence time to do something useful. And we'll come back to what these errors are, but it's fundamental to qubits. Okay, here's the processor that we made. It has 54 of these cross kind of qubits that I showed before in a rectangular array. And in between all the qubits, you have what's is an adjustable coupler. I'll explain out in a minute that can turn on and on the interactions. And the nice thing about making a square array with 4 nearest neighbors is it's forward compatible to do something called error correction with the surface code, in which case you can measure and correct for the errors, and you can get rid of this finite coherence time. And this is very important in the long term, and in fact is why we did this experiment with this architecture to be forward compatible to all the experiments we want to do in the next 10 years. And here's the chip. You can see that there's a bump bonding between what's essentially the qubit chip, and here that's the wiring chip, and that's thousands and thousands of indium bump bonds. And then the wires come out to the outside, and then we wire bond that to a circuit board. And you can see that here in the circuit board, this is wires that go to an array of microwave connectors at the outside. And then in the center, we have some shielding for infrared and magnetic fields so that the qubit works better. So this device with 54 qubits and all the coax connectors along the outside are then put on the inside of a dilution refrigerator. This is about 0.7 meters across. It's fairly big for a dilution refrigerator, but nothing you can't do. And then these wires are connected to various filters to room temperature electronics, and also connected to room temperature quantum limited amplifiers to do the measurement. And this is at about 10 or 20 millikelvin, which is a temperature, an energy KT that's much less than h bar omega, which is about 200 millikelvin of the energy of the qubits. And thus you get rid of all the thermal effects. And then all those wires come up to the top of the cryostat and then go into racks of electronics where we generate the microwave pulses and the other DC pulses used to do it. These are gigasample per second D to A converters, and densely put into cards and into a rack to allow us to do many channels. And of course, the big part of this is the entire software stack that you use to control those digitized waveforms and vary it and communicate with the qubit and read it out. And that's a tremendous amount of work to do all that. To talk a little bit about the coupler, basically we have qubits, and we basically make an adjustable capacitive coupler from one qubit, given here in kind of a differential form, and then to another qubit as its nearest neighbors. And this circuit here is basically an adjustable capacitance, and we essentially use a swapping operation of two coupled oscillators, which is analogous to coupled swings or coupled electrical oscillators. So it's almost classical-like in how you understand it. The basic idea here is you have a qubit that's capacitively coupled to another, it would be a qubit, that's at a higher frequency than the regular qubit. And with this slightly off resonant, it rings up a little bit. It drives this so it's virtually rung up a little bit, and then that drives the neighboring qubit. And by adjusting the frequency of this oscillation, which we can do by putting in currents here, we put a current that changes the inductance and changes the qubit frequency. We can also change the frequency of our coupler through this current bias line. You can then change the amount that's ringing up and change the amount of capacitance, the effective capacitance. Since this is higher frequency than this is an inductive response, and this gives you 180 degrees phase shift from left to right. So it's a negative capacitance. And if you set that negative capacitance properly, and and of course add it to a fixed coupler capacitance, which is positive, at some bias here, you can get zero net coupling and turn it off. And that's really important to be able to zero it in building a complex system. This is some data. This is actually real data that we've taken testing how this works. And what we do is we have the two qubits and then put in a NOT gate to make one excitation and one qubit. And then we put the two qubits on resonance and turn on the coupler, and we watch that excitation oscillate back and forth between the two qubits, just like coupled oscillators classically that you know how that works. And then we turn off the coupling and measure if it's in the neighboring qubit. So this is a plot of population transfer from Q0 to Q1. Initially, there's no transfer, and then it gets transferred and then comes back. And you can see the oscillation here between the two states, which is pretty clean. And then if you change the coupler bias, you put current into this device, the oscillation frequency gets lower. And then at some point, you don't see an oscillation at all, and that's where the coupler is turned off. And then you go a little bit beyond that, and then the negative capacitance is dominating, and you can turn it on quite rapidly right here. So it's nice in just a few nanoseconds, you can turn off and on and off this coupler, cause the swapping to activate and couple together the two qubits to make a logic gate out of that. Okay, so now I want to talk a little bit about how well do these gates work, and I give you a rough idea, but we have to measure them very carefully. So the first thing we do is we take a qubit, all the other ones are off resonant, turn off the couplers, and we measure its coherence, and we measure per gate what's the error of it. And the way we do that is measure the total error of a sequence of gates as we vary the sequence length. and knowing how many gates we have and how the errors are increasing over time, we can get a per gate error. And that error is roughly about 0.1%. We can do 600 to 1,000 operations or so before we lose the coherence of the qubit. And that's kind of consistent with other measurements and what other people have done, and it's right. Now there's a distribution as we look at all the other qubits here, and you can think about that as a pseudo-Gaussian, almost Gaussian distribution. We like to integrate that distribution because that gives us a little bit better information, and that's given here in the dotted black lines. And you see that it's mostly, on average, it's about 0.15%, and then there's some statistical spread between them. Now, of course, that's operating it one at a time. And when you want to build a real computer, be it classical or quantum, you want to be running your gates in parallel. It's simultaneous, right? Because that's how you're going to speed up the operation. And you're not going to make a conventional Turing machine where you do one operation at a time. You have to make it more efficient. So we have to do the experiment, same experiment, but now we're simultaneously turning on all of our qubits. The couplers are off, and then we see what happens there. So we do the same experiment now with 53 qubits at the same time, and we get the black line. Now, of course, you expect that there to be some degradation because there could be crosstalk and other imperfections in the system. And what's good to note here is that even though you're doing it simultaneously, it's worse, but just a little bit worse. You go from 0.15 to 0.16. So that's all good. Things working well. We know that we have good isolation, and it's really taken a long time to figure out how to do that. Now you can do the same thing with two coupled gates, turn on two and turn on the coupler as I showed before and get an error per 2 qubit gate. And then you do it simultaneously where you're running pairs of these gates. And when you do that, you get the solid green curve. And the solid green curve is a little bit worse than what you expect just from the single qubit gates. When they're isolated, yeah, it's more or less what you expect. When you do it simultaneous, there's a little bit more crosstalk. So again, you have to track that down, make it better over time, but it's not too much worse. And you can certainly build complex algorithms based on that. So that's good. So we can characterize the device at the single and 2 qubit gate levels. Things work right in the simultaneous mode that we want to use the quantum computer. But the question is, when you run a complex algorithm and using all of them at the same time, are the errors going to get worse? Are things going to happen? And that's essentially what the experiment does that we work on, is test for that, see what the system performance is. Before I get to that, just let me say that the big problem here is calibrating these gates, especially when you have a big system. This is a calibration graph for 1 qubit or 1 pair of qubits, 2 qubits. Okay, it's quite complex. You have to do a lot of stuff to get everything tuned up right. Just to give you a sense of the magnitude of this, these 2 dots, it was the PhD thesis of one of my students at UCSB. And basically, he took all that knowledge he gained during his PhD and wrote code, software code, to automate that, which kind of puts you out of business as a graduate student, but it's nice because now you can do more interesting things instead of calibrating qubits all day. So this is what you have to do. It's a lot of work, but you just build up this knowledge, and you can calibrate these things automatically by doing the right calibration. So for the quantum supremacy experiment, for a general computation, we're running this simultaneously. And I want to show you the general purpose algorithm on the right, where the single circles are the square root of naught gates or single qubit gates. And then we have a line between 2 qubits that represent the 2 qubit gates that I showed you before, this kind of swapping operation. And with the combination of those two, you can build a general purpose algorithm and run whatever you want like that. And we're going to use this general purpose circuit algorithm like to do the quantum supremacy experiment, and I'll discuss that in a second, exactly how that works. If you take a center qubit here and think about what's going on around it, that's given in the lower diagram. We start off in the 0 state, then we do the square root of naught gates, only we do it at 3 different angles, 0, 90 degrees, and 45 degrees with the microwave phase. And then in the next sequence of the cycle, we will connect to it a neighboring qubit with this square root of swap operation I showed you before. And then over time, it's more square root of knots, a single qubit, and then 2 qubit operation to another neighboring qubit, and then we just cycle through them and then repeat. And then at the end, we do a measurement, and that tells us the qubit states. Over here on the right, I just show you that the 2 qubit gate is about 12 nanoseconds in length, while we change the qubit frequency in the coupler, and the single qubit gate's about a little bit longer, 25 nanoseconds. Kind of amazing that the 2 qubit gate is faster than the single qubit gate. That's of course very useful, but the adjustable couplers really allow you to optimize it that way, which is part of the reason we went to it. Okay, quantum supremacy experiment, it basically checks this general purpose circuit. And what we do is we build the circuit interleaving square root of naught gates and with 3 different angles randomly chosen with the square root of I-swap gates. And you're basically running a pseudo-random quantum number generator, okay? And then where we measure a state at the end. And doing this, you get all the possible outputs of the states. What's interesting about generating the states this way is that some states are more likely than others. And the analogy to use to understand that is like laser speckle, which I show here on the right-hand side. Laser light going through frosted glass, it diffuses out, but in some directions, the light is brighter because of constructive interference of the waves. In some direction, the light is dimmer because of destructive between the waves. And the same thing happens with qubits. If you have coherence in this system, some probability, some numbers, output zeros and ones, will have higher probability and some will have less. Okay, and we use that fact to test the quantum computer. And what we do is we run the quantum computers and we're going to preferentially sample the high probability states. And then what we do is we simulate the exact same circuit in a data center or a big supercomputer to compute the probabilities. And then we check if the ones we measure were the high probabilities. And you can see the formula we use to check right here. We basically take the states that we measure and look up here what the probability is. And if the probability was 1 over 2 to the n, no correlations and no coherence at all, then the fidelity is 0. But if you have this speckle going on when you work through the math, then this fidelity turns out to equal to 1. So 1 is a perfect match, 0 is errors. In fact, if you have any error in the quantum circuit, you're going to get a 0. So if you have 1 bit flip or you have 1 phase flip in the algorithm, you will get 0. And what's nice, and this is a really nice metrology tool for testing systems, is this allows you to test if your quantum computer and your whole software chain, you made an error in your software coding, you'll get fidelity to 0, you'll notice that, and then you'll go ahead and fix it. If you have 1 error in the coherence, you'll know that, and that gives you valuable information. So this cross-entropy fidelity is very useful in terms of system validation. And in fact, you can learn the control map of the system, get lots of information out of the system. So it's a very important tool to check for your system. Okay, so here is the data that we take. We run it on a variable number of qubits, starting with the small subpatch of them of 12 qubits and going all the way up to 53. And this is for 14 cycles. So that's 15 square root of naught operations and 14 neighboring 2 qubit interactions. And at 12 qubits, that's something like 250 gates. And I told you that the fidelity was roughly 0.1%, maybe a little bit more. So it doesn't surprise you at all that the total fidelity of the system is about 40%, pretty high. Almost half the time it works properly, but because there are gate errors, it doesn't work all the time. And so that's the red circle here. And then we just increase the number of qubits. And of course, more qubits, there are more chances of error. The errors should go down exponentially when you think about the classical statistics, which it does. And then it goes down here. And finally, at 53 qubits, we have a red circle there. And this required a big data center to analyze the data properly. Up to about 30, it's a laptop, and then a workstation, and at the large numbers, it's a big data center. So it's going down. This is statistically different than 0. Everything looks okay. Just to talk a little bit, we can check this data in some different ways. One is you can take this big circuit and then just cut the I-swap interactions between the two. And it's nice because that's more or less the same number of operations, but of course, it's much easier to calculate because the quantum size is half as big. And since it goes exponentially, it's a very easy calculation. So you can show that the blue crosses basically line up with the red circles very nicely. And you can kind of do something in between where you cut out a part of the gates in between, and there's some mathematical way to do the simulation that you can still simulate that relatively efficiently. And for the lighted circles, which is the cross marks, again, agrees well with the data. And again, it's because it's more or less the same number of operations. So that all chalks right, and you can figure out what's going on here very well. Of course, what you want to do is get far into the supremacy region. And it turns out that this particular sequence of neighboring gate operations, there's a mathematical trick that allows you to calculate that more efficiently. But if you go to a slightly different sequence, you can't use that mathematical trick anymore. And then it turns out to be much harder to calculate. So the data here is we use that trick, and this is number of cycles with 53 qubits. And again, this is going down as you expected here. But now there are no red circles because we can't calculate this anymore. The time to calculation would be weak to thousands of years. And you just, okay, you can't check your data. However, you can check it by proxy by looking at the patch in a lighted circuit, which we saw here was a good proxy for what the red circles will be. And that's given here, and that's not too hard to calculate. And you see even with phi sigma error bars, it's significantly different than 0. So we know that at one time, it's working properly for some appropriate fraction of the time. I also want to point out, so this is great, it shows that we've done a powerful computation. We can check it and make sure it's okay, but still do the computation. The one thing I would like to also show here is that the black line, and the black line is the prediction from the gate and measurement error. So this is exactly what we expected from the 1 and 2 qubit errors that we saw previously. And then let me talk about that and some other things next, which is important. What is the scientific meaning and results of this experiment? What's the quantum science results? First of all, it's very interesting that the full and elided and patched and predicted basically gave the same fidelity. And this is very interesting because it says that the errors that you see in a complex quantum computer system does not agree on the degree of quantum entanglement and computational complexity. It's given by a much simpler concept, which basically means that this computation complexity entanglement is not going to limit your quantum computer in some way. Okay. The other thing is the prediction agreed very well. And that means there's no new decoherence physics. So the prediction came from the 1 and 2 qubit data I showed you previously. And all we do is take those errors and measure the fidelity, which is 1 minus the error, and then multiply all those fidelities by varied gate operations. This is classical statistics that you learned in high school. Okay, very, very simple idea. Classical error calculation. And we see that that's very predictive. And of course, that's really good that it's so simple. And then that's all very good because this is the kind of statistics people have assumed and had to assume in order to do error correction and go on and build a quantum computer. So this is very good, and this is strong evidence that error correction should work. Quantum mechanics works, and here at 53 qubits, it's a huge 10 to the 16 Hilbert space. This has previously been tested to about 1,000 states or so. So we've really opened up the validity of quantum mechanics in this way. For the experts, let me just say that you can test the ideas of digitization of errors, which is central to getting error correction to work. And by doing that, you can show that this idea of a digitized error is correct, even in the middle of an algorithm. And I think that's very important because, again, it further tests the assumptions that you need to build a quantum computer. So now in the last 5 minutes or so of my talk, let's discuss a little bit about some of the applications. Obviously, people are building systems. It's very interesting that you can run algorithms. Here is a case where we've done quantum chemistry on a Sycamore device. You basically take your chemistry problem and you compile it into qubits, in this case, using a series of assumptions here. And then you run a quantum circuit, which is basically this variable swap circuit that I showed you. And it's one of the reasons we were quite interested in this, is it directly maps into running this. And you do a variety of measurements and a variety of thetas here. And then you can use some conservation laws to correct imperfections. And even though it's lots of operations and the computational fidelity is low, using these conservation laws, you can get a net fidelity that's actually much, much higher by doing that. And then variational optimization to improve the answer. So that's the basic idea. Here's some data on, there's a H12 molecule, a string of hydrogen atoms. It doesn't exist in nature, but it's a good, simple computational problem that allows you to check this. And the blue dots are the quantum computer, and the black line is the classical computer, and they agree very well. And the error between them is very low. In fact, if you just go down to H6, the errors in that case are within what's called chemical accuracy, and it was a perfectly good quantum calculation to know the energies as well as you would need them. And just this is double the number of qubits electrons prior to largest chemistry simulation, more than 10 times number of gates. So, you know, it's really doing a big advance in doing practical things. And what's nice in this whole system here at Google, they have Open Fermion for doing this chemistry to qubit translation. We have programming, open source language circ for coding it up, and then we run it on our quantum computer. So we have a package here, and obviously setting this up for people to use it as a quantum data center, and some people are beginning to use that. And we've done a variety of experiments here, and I think the thing I really want to point out is that the experiments we're running on this system-wise, we're running hundreds to thousands of total number of gates at this point. We have enough control, we have enough fidelity of the device that we can actually do sensible operations here and do complex information processing. And I think this is really nice because this quantum computer, these algorithms, other quantum computers can be simulated classically quite straightforward now. We're not at this quantum supremacy limit of useful applications. However, by the time you're up to 1,000 gate operations, you're running real algorithms, you're testing how the algorithms work, you're thinking about how to do error mitigation. So this is large enough to really push your algorithms and test them carefully. And that's a really good era to be in because people will then be developing it on the software end much more effectively, because they're doing complex real tests, and that's very exciting to see that that's happening. We want to improve the qubit, and you're going to need to improve the qubits and the system to do more complicated. You want to have more qubits, you want to have better qubits, and you want to do error correction in the long term. So, basically you have to decrease the seeds errors to 0.1%. Let me state that the T1 of the Sycamore device was 16 microseconds. This is nowhere near the limit of superconducting qubits, and we're kind of limited by this coherence time. So we have to, make the coherence better. This should be possible. It's kind of hard when you build a complex circuit, so we have to figure that out. But I'm very optimistic that this can be improved and the errors come down there. We have to also improve the measurement errors too. And then there's a variety of other things I've been thinking about on my own, information constraints on scaling, cosmic ray events, and gamma ray radiation. But although on average are quite small per event, it's a huge problem. You have to fix it in total by a factor of 10 to the 6 or so. So we think we know how to do that. People are doing experiments, and that's looking good. But we have to figure out how to make the systems better. And then there's leakage-induced correlated errors, a recent thing showing how to get rid of two-state errors. So there's a lot of progress. We have to make the qubits better, but things are working well, and we know how to do the next steps. So at this point, I'm basically at the end of my talk, maybe a little bit earlier. That's good. I'll have more Q&A time, just with the summary and outlook here. First of all, people are building complex quantum computer systems now, and we built one 53 qubits. This can be made bigger in the future. But the good news for the field is that as we build these complex quantum computers, they're working as expected, computing on this large Hilbert space. And there's no new fundamental physics. And at least for how we're building the device here, we don't see that there's any practical engineering or other dirt effects that's causing problems. So that's good. Now, we've done a powerful computation and shown this. The next thing we want to do is do something useful. And many people are working on this. And of course, this is going to have to be with probably improving the hardware and also inventing algorithms so that they're compact enough that they can be run on near-term devices. And people are going to do both. And it's just a very exciting time for the field, because as these things are getting better in both directions, are we going to come to a time where we can actually do a useful algorithm and really set the field in motion commercially to do something useful and to start using these for practical applications? And it could be this year, it could be tomorrow when I open up a journal, it could be in a few years, or maybe take longer, 5 years. But we're at an exciting time where this can happen, and people are working hard on it, and we'll see what happens. And also, of course, we're working on error correction where we know we can run it, and that's going to take longer, but again, there's a path for that. And again, it supports both investment in people putting money into it. It also supports people working on the problem and investing their time and careers to do this. And we're very pleased that all this work is happening. People are working to build complex systems, kind of the next frontier of the field. And we'll just see where it goes. It's a really exciting time, and we need to be working hard on this to try to build it. It's very hard to build a useful quantum computer, but certainly there's all this motivation from data, experimental data, to say we have to work hard doing that. With that, thank you very much, and it's my pleasure to talk about this.
Great. Well, thanks a lot for the fantastic talk, John. We have a couple questions in the chat, and I'll ask them in just a moment, but would like to encourage folks who do have questions to please type them in the chat as we go along, and we'll get to them all. So the first question is from Milos. He asks, when you say the qubit is an oscillator, is that what you mean, or do you mean it's a resonator? I think this is from electrical engineering.
Yeah. It's more of a resonator than an oscillator. But of course, when you put in an excitation, it's oscillating in a quantum mechanical sense. I think the basic idea here is that it's almost a linear oscillator. It's just slightly nonlinear. And because of that, from the electrical engineering point of view, the wave functions look like your photon wave functions that you study. Looks like a harmonic oscillator wave functions. Of course, there's some nonlinearity there, but it's kind of nice because if you're an electrical engineer, you can understand maybe 60 or 70% of what's going on with this device by thinking of it just as a simple oscillator. And you have to put quantum mechanics on top of it and the nonlinearity on top of it. But you can do a lot of engineering work by just understanding it as an electrical resonator or oscillator. So that's kind of why I introduced that concept. And that, of course, makes it nice because you can engineer a system a lot easier if you can use some classical analog.
Okay, so the next question is about the bit size of a qubit. So the question is basically they wrote, I'm assuming the bit size limit for a quantum computer is variable, unlike a classical computer, which is binary. And I guess the question is that true?
Yes. So most all real quantum systems that you look at have multiple states. So in this, it's like I said, it's an oscillator. You have the 0 and 1 state, but you also have the 2, 3, and 4. Now, in our view, those extra states are an annoyance, and we have to do things to make sure we don't see them. However, you can use that as a resource. In fact, we used the 2 state as a resource to do our controlling swapping gates in some way. And then there's people like the Yale group are trying to use those sequence of harmonic oscillator states to encode information and to hopefully build a more efficient essential qubit system out of it. So that can be used. And it depends on the experiment whether it's an annoyance or not. But you have to worry about those states. In fact, one of the recent papers I talked about tells you that in the middle of a sequence, you reset the 2 state to 0 so that you don't get correlated errors, which is very bad for quantum error correction. So people are starting to do algorithms where you're actively getting rid of those extra states because you really don't want them there.
Okay, next question is one that we were talking about earlier, John. So Andrew Dane asks, can you give us your perspective on materials and fabrication used to make these devices, and what's the most important problem that needs to be solved in that domain?
Yeah. So yeah, great question. What happened in running up for this quantum supremacy experiment? We had pretty good qubits, but we weren't worried about materials at all. Is to build this complex stack of qubits and get everything to work was a hard enough. And we had a relatively small group for the industrial effort at the time. So we were just totally focusing on making the chip, getting the 53 qubits to work, having small crosstalk, and fixing all the systems problems. So we were thinking about systems problems for maybe 5 years, okay? And and the coherence was good enough to do the experiment. It was 16 microsecond T1, which is not horrible, but it's nowhere near record. So I'm going to say now that that's been done, of course, there are Google groups working on other things. They're now going back and trying to figure that out. So that's something I've been thinking about, the Google group, other people. Again, you're making a very complex chip, so it's a lot more complicated to make long coherence because you can't make simple assumptions that you make when you're just making a single qubit. So, it's being worked on. I've been thinking about that. I very carefully listened to the March meeting talks and listened to the talks by Will and the MIT Lincoln Lab group because they have a lot to say. And, I have a bunch of ideas on what we want to do. I just posted on arXiv part of those ideas. And that's what we have to work on now. In my view, that's the most important thing. If we can get the coherence up to 50 or 100 microseconds on a 50 qubit device or something of that order, my view, and then you should be able to do good error correction. In my view, you've now shown a scalable way to do things. It should have good, low enough errors. And then that's a very strong motivation that error correction would work. So, that's the next step for me, at least. But it's hard. Okay. So, getting a complex chip to work is hard and that's what we're doing next. So at least I'm focusing on, I know Google's working on it hard.
Indeed. The next question is more of a fundamental question. And Jin Chen asks, what's the difference between a quantum computer and an analog computer?
Yeah. Yes, it's great. Actually, I like the question because you have to think of a quantum computer as an analog computer. You're putting on analog pulses. If the height of the pulse varies, then you'll get a different gate and the like. So it's fundamentally analog. And then what you're trying to do with error correction is to turn it into a digital quantum computer where there are no errors per gate operation. So that's the way you do it. And this is like classical electronics, where your transistors and your capacitors and your resistors, they're fundamentally analog. And then you use some gate configuration, basically using some kind of feedback, okay, that turns that analog system and digitizes the answer for you. So I think it's quite analogous to classical computing in the kind of the different levels of abstraction that you go at it. Obviously, the quantum computer is deeper and richer and the like, but that's the way you think about it. So, given that, I'm an older physicist, and I learned electronics back when it was mostly analog. This is very natural for me to think about the system, and then you put digital on top of it. So you have to, for example, when you think about the phase errors, you think about phase noise, and error correction is kind of like a phase locking feedback system. There's a lot of nice analogs with classical systems that you can use to understand what's going on. And I think that's good because you need those engineering concepts to, be able to properly understand the system.
Next question is from Yu Ting, and he's wondering if you can comment on different platforms like superconducting qubits, trapped ions, neutral atoms, and what you think the first quantum computer will be.
Yeah, so this could be a very controversial question, okay? But what I've always said is that it's very good for the field that we have all these different approaches because they're going to have their benefits and challenges. And then by understanding that, we will then, it's more likely that someone can build a quantum computer, okay? Because that's, in the end, what we want to do is have success. I say this, it's not time to down select on anything because the basic problem is we don't know how to do quantum system engineering yet. We don't know how to take, the few qubits that we're making and build a big system. And until we start doing that and really understanding, that's fine. Now, I think superconducting qubits are far along with that. People know how to do ion traps. There are other systems, and then it's fine. But let me say, if someone can build a qubit system where they can get their single qubit errors, 2 qubit errors, measurement errors down really low, then you really got something regardless of how it's going to scale. And that's because right now, let's say, the 2 qubit errors typically are a few percent. Okay, and then if you work really hard and do special way like we did, you can get it down lower. And if someone could take those errors and bring it down 10 to minus 3, 10 to minus 4 or lower, that totally changes, how you think about it. And then, it's worth doing the scaling challenges. So I would say, it's all open right now. And no matter where you are in the progress, if you can make really good qubits, and not just 1 or 2, but, let's say 5 or 10, right? So you're pushing the scaling a little bit. Show that you can make it work well, then you really got something. So I'm just, really advocating people do those experiments and do that. And like, for example, at Silicon Quantum Computing here in Sydney, they have the 10-qubit device that they're playing with, and they understand that, and they're really working to try to figure out how to make good devices at that scale, which I think is very appropriate.
Next question is about applications, and I'm going to paraphrase it, but basically, what sort of applications, or what do you think is the killer application for a quantum computer, or the first commercial application?
Yeah, great. Of course, this is more theory, and I'm focusing on building it. But what I think, the field is in a really good shape right now because there are two general classes of applications. And one is for sure, but it's a little bit nichey. The other one is very broad, but it's harder to get there. But that's a good balance of application. So the application I always like to talk about, which I did talk about, is the quantum chemistry. And right now, that's a big field. I don't know, 15, 20% of supercomputer time is used to do quantum chemistry because it's a hard computational problem. And if we can build a quantum computer to solve that efficiently, then we'll be able to do a better job designing molecules and like, we won't have to synthesize them in a lab. You can understand them, with quantum calculations as you normally do. And I can imagine there's a huge technological benefit from that to, be able to simulate quantum mechanics in this way. And, people talk about nitrogen fixation, ammonia, and do new materials, how to make better batteries, a whole host of things. But of course, it's a little bit nichey. It's very scientific, but certainly there. And what I like about it is that people know what the algorithms right now. They know what you have to build. And for example, there's a Google project to build a 1 million qubit error-corrected quantum computer. And if you can get that to work, you know that you can solve untractable quantum chemistry problems. Okay, so there's a very fixed, understood, we know, and it's going to get better over time. People are inventing new things theoretically, but we know what we need to build. And we know in the end, we can do something useful. Yeah. And I'm going to say, even if it's just that application and we spend billions of dollars with it, if you make new materials that solve really important problems, it's worth it, okay? The other thing people are looking at is, the name of the Google group is Quantum Artificial Intelligence. It's basically to do AI, and it's basically to do fitting to data, okay? You have a bunch of data. AI is just building a mathematical model that fits very complex data efficiently. And if you can do that with a quantum computer and solve these practical problems in AI. And one of the examples given there is the traveling salesman problem. This kind of optimization problem is used in business all the time. If you can get a 5% improvement on allocation of resources, that usually translates into billions of dollars and can be very big. Now, it's great, it's a big application. The hard part is that there's no known algorithm that's going to work and do that. But for example, with AI got invented and used widely without people knowing exactly how it works properly. And many of these algorithms are heuristic. They just work and they give better results and it's okay. So you can kind of see that's how quantum works. So there's a big chance there that you can do it. And if it's true, then that's going to make a very big impact because these kind of optimization problems are everywhere. It's big business. So, in some sense, that's driving a lot of the investment. But I'm saying, even if that doesn't work out for some way, or it motivates better classical algorithms, which is just fine, okay? I think we still have the chemistry algorithm to back up, and we'll definitely do something with that if we can build the quantum computer.
We have one more question, and this is from Justin. And it's a question I often ask myself too, I think, and I'm sure you do, John, which is, would the required number of signal generators, or AWGs, become a problem for further scaling up the system? And do we expect an architecture change in the future?
Yeah, a great question. I have a small one-page paper on this that I mentioned here. It's on my Quantala.com website. And one of the things I'd like to mention is, you would like to multiplex and to make less classical resources available. But people have to realize right now that the errors of the qubits are not as low as we want. And what happens is if you build some multiplexing system or whatever, you don't quite have the control that you need to completely optimize it. And you're generally going to give up some error if you're going to multiplex, because you just can't optimize it super well. Now, if we were way far below the threshold, we would have something to give up. And you can imagine building such control systems. But if you have to make the qubit control better and the qubits better and multiplex at the same time, from a system engineering point of view, you're really asking too much, okay? So again, we need to improve coherence and errors so that we can do this kind of multiplexing and get it better. That's why I always say coherence and errors are key, because that's going to allow you to solve things in many ways. My particular view is that you're always going to want to improve the control and lower the errors. So thinking about scaling up by having generators and control on each channel is not something you should discard. So in the way I think about scaling, that's something I'm thinking about. And I think one can do orders of magnitude better in the cost and the size of such control systems. And that's something that I would like to work on and I think is important. So I think we have to work on all these fronts and then kind of see what happens with the system engineering. And it's kind of funny to think to scale, you need better coherence, but this is well known in engineering circles. You need margin. You need to be able to trade off things, and we're just not there yet. We need to everything needs to get better. But people should be thinking about all this. It's really great. It's kind of it's a nice era right now because we understand basic things. We have working systems, and now we can see a lot of the details, not details, that's the wrong word, engineering we have to do. And it's great that there's a lot of engineering disciplines that are getting involved in it. And that's going to help us solve all these problems. So it's a nice time for the field.
Okay, one last quick question just came in. What is the photon lifetime in your superconducting qubit resonators?
Yes, so that was 16 microseconds. And then I think the Google group has gotten that up to 20 right now. And in the field, like at Will's group and others group, 50, 100 microseconds, even longer is quite common. So, we feel optimistic we can get that factor, but of course it's complicated when you build a complex chip. You have to understand a lot of things to do the systems engineering. So we feel optimistic, it just has to be solved.
Yep. Great. Well, John, thanks so much for taking time today to speak with us at the MTL seminar. Really appreciate, hearing your talk on quantum supremacy. And looking forward to seeing you in the real time, in the next time, in the future.
Yes, I have to come visit your group. There's a lot to talk about. And that's what I learned at the March meeting. To really need to sit down with your group for a couple of days, and that would be great. Eventually, we'll get there.
Yeah, well, we're looking forward to it. So thank you, and thank everyone in the audience for showing up today. And have a good day, John, and have a good evening, everyone here.
Yes, bye-bye. Thank you again very much. Bye-bye.